Today we are going to discuss nuclei. In this, we'll do first of all what are nucleons, what is nuclear size, and how nuclear size is related with the mass number. After that, we'll see how nuclear density is expressed and how it is related with mass number. Does it depends upon the mass number or not? And then we'll do nuclear forces. After that, we'll do mass defect. What is mass defect? And then we'll find what is expression for binding energy. Then the binding energy curve with the mass number. And what informations and the inferences we can get from binding energy per nucleon plot with the mass number. How we can explain phenomena of fusion and fission from that. So all these we'll discuss in today's discussion. First of all, let's take what is nucleus. Nucleus is the small space inside the atom where whole positive charge and almost entire mass of the atom is concentrated. So that part we take it as the nucleus there. And in the nucleus, we have protons and neutrons there. Electrons are outside the nucleus and they are revolving in different orbits there. So nucleons is another term which is used. Nucleons are the constituents of nucleus. So basically we have the protons and neutrons lying inside the nucleus. So we take the proton and neutron as the nucleons. Another term which we get, that is the nuclear size. Of course, nuclear size will be related with the nuclear radius, what we express. Now that term, that is the nuclear size, it is found to be related with the mass number by the relation R proportional to A power 1 by 3. R is the nuclear size here, that is you can call it as the nuclear radius, and A is the mass number. So here we can write this R as some proportionality constant will come when we remove this proportionality relation. So this is your R naught, A power 1 by 3. Now this R naught is a constant, proportionality constant. But there is a very unique thing about it. This value of R naught depends upon the type of nuclei, what type of nucleus it is. If it is your lighter nuclei, in that case its value is something different. If it is mid-range nuclei, it is different. For heavier one, it is different. In fact, the value of R naught ranges from 1.1 Fermi to 1.3 Fermi. But normally, as an average one, this R naught is taken as your 1.2 Fermi. So it is 10 to the power minus 15 meter. So 1.2 into 10 to the power minus 15 meter, that we take it as the average value for the R naught there. But again, do remember that this one's value ranges from 1.1 to 1.3 Fermi there, depending upon what type of nucleus we are taking. Let's take another term, that is the nuclear density. It will be basically nuclear mass per unit volume. And there we can take mass of the nucleons there per unit volume as nuclear density. So suppose if I take that M is average mass of the nucleon and A is the mass number. R is the radius of the nucleus. So if M is the mass of each nucleon, A is the mass number, therefore mass of all nucleon, this will be M into A. So volume of nucleus, this we can take as a solid sphere. We can assume it is like a sphere and radius is R, so it is your 4 by 3 pi R cube. Now we know that R is R naught a power 1 by 3. So in that case, the volume term will be equal to 4 by 3 pi R naught a power 1 by 3 whole cube. So this is 4 by 3 pi R naught cube into A. So now if you take the nuclear density, in that case, the nuclear mass, that is your M into A, divided by the volume, which is your 4 by 3 pi R naught cube into A. So now here you can see that A will get cancelled and you will get 3m by 4 pi R naught cube. Now here, this is the mass of the nucleon. R naught is the constant which we have used here. So that way, this nuclear density will be constant. But here, I will suggest that better you conclude from this that nuclear density is independent of mass number. Of course, indirectly it will mean that it is not depending upon the nucleus there. One nucleus to other, it will remain the same. Now, why we are saying that? Because this R naught you are taking constant. If you say that this is constant, and if this is constant there, we have seen that R naught value will range from 1.1 to 1.3 for me. So here it is best that you say that it is independent of mass number, because A term is getting cancelled. Of course, indirectly it will mean that it will be same for all. But just for a case, if you want to see what value we get for this nuclear density. So if you just substitute value, if you take, how much it will be? 3 into 1.67 10 to the power minus 27 mass of nucleon. That means you are taking mass of the proton or neutron there. So this divided by 4 pi into R naught. We are taking value of 1.2 Fermi whole cube. This is equal to 2.31 into 10 to the power 17 kg per meter cube. This is the nuclear density. Now you just compare it with the density of water. What value of the density of water we take? 10 to the power 3 kg per meter cube. Now you just compare how dense it is. Density is roughly about 10 to the power 14 times. So that is why you will find that the nuclear density will have very high value there. Nuclear force. This is the force which is responsible for keeping all the nucleons together in the nucleus. You know that in the nucleus we have the protons and neutrons. Protons are there which are positively charged. So between the two protons there will be repulsive force. That is the electrostatic force there. And gravitational force is also there, but that will be attractive, and gravitational force cannot overcome electrostatic force, because the gravitational force value is very small as compared to the electrostatic. And electrostatic force between two protons will be repulsive, but still all the nucleons are together in the nucleus. So how it is possible? This is possible because of the nuclear force which is acting there. Nuclear force is a very short range force there. And in fact, if you plot a graph between the potential energy and the separation between two nucleons, then you'll find you'll have the plot like this. This is indicating when the separation is large relatively. Of course, all these are in Fermi there. So in that case, the potential energy will be negative. And there, the force will be basically attractive in nature there. And as the separation is getting decreased, in that case, definitely that potential energy is decreasing. And it will acquire a minimum value there at the separation, say R0. This is the point where you have the nucleons there in the nucleus there. And there the force is definitely attractive there, which is overcoming all the other forces there, like the repulsive force due to the electrostatic force there. But here if you decrease the separation further between the nucleons, in that case the potential energy will start increasing. That means the force will start getting decreased there. And this is the point where the force or two nucleons, if you consider, that will become potential energy will be 0 there. So after that it will start getting changed to positive value. That means now the force there will be repulsive. So from here it is the minimum energy where it has the equilibrium there, or you have the formation of the nucleus there. But if you are decreasing the separation further between the nucleons, the force will start becoming less attractive. That means positive force will be there. That means it will start becoming repulsive there. So beyond a particular separation, if you are decreasing that further, the force will start becoming repulsive. This is the reason why if the force between two nucleons is attractive, they do not combine and they fuse together. So there is a boundary there where it will prevent it from getting fused. That means there will be a separation maintained there, and the nucleons will be there at particular separation there in the nucleus. Still, that force which will be attractive in nature will be responsible for keeping all the nucleons together in the nucleus. Now, if you take the properties of the nuclear forces, first property is that it is the strongest attractive force. So in nature, if you see the different forces there, this is the strongest force and it is attractive in nature. Second is, it is a short range force. Nuclear forces, although it is attractive in nature there and they are the strongest force, but they are the short range forces. So also it is also called it shows saturation property. It means it will be acting there to the nearest nucleons there, and it will be a very short range force there. Another is that it is the charge independent force. That means if you take two protons, between two protons there is nuclear force. Between two neutrons also there is nuclear force, and it is also between a proton and neutron. So it is not depending upon the charge, it is acting between any two nucleons there present in the nucleus. So it is the charge independent. But it is spin dependent. It depends upon the spin of the nucleons there. So it will depend upon that. Another property is that it is a non-central force. Nuclear forces are non-central forces. We have other forces also there, like you take the gravitational force, electrostatic force, all are the central forces. But this is your non-central force. So these are some of the important properties of nuclear forces. Mass defect is difference in mass of all the nucleons and that of the nucleus. In fact, you will see that if we have the different nucleons forming a particular nucleus, then total mass of all the nucleons forming that nucleus, if we consider, and we compare it to the mass of the nucleus which they have formed, there is some difference in the mass. Some mass disappears, or it is less there. So that particular mass which is there, which is missing there, basically it gets converted into energy and it is released from the system. So as it is released, definitely it will be now more stable because their energy will get decreased. So if you consider the mass defect, it is the difference in mass of all the nucleons and that of nucleus. So difference in mass of all the nucleons and that of the nucleus there. Let's take expression for this mass defect. So we are taking expression for mass defect. Suppose we take that Z is the atomic number and A is the mass number. whereas MP, Mn and M we take as the mass of proton, this as mass of neutron, and this is the mass of nucleus. This is your atomic number and this is the mass number. So here, if you consider the mass of all the protons, we have Z number of protons there because atomic number is Z. So mass of all protons, this will be Z into MP. Mass of all neutrons, if you consider how many neutrons will be there, if A is the mass number, Z is the atomic number, so A minus Z will give you the number of neutrons. So this into Mn will give you mass of all the neutrons there. So total mass of all nucleons, how much it will be? Z into MP plus A minus Z into Mn. And we have taken M as the mass of the nucleus there. Therefore, mass defect, this will be how much? It will be your Z into MP plus A minus Z into Mn minus M. That is the mass of the nucleus. So this is the expression for the mass defect. So we'll get this expression for the mass defect if you know what is the mass of the proton, mass of the neutron, and for which particular nucleus we are taking, what is the atomic number, what is the mass number there. There is a term that is the binding energy. In fact, this will be the energy which will be released when nucleons are forming a particular nucleus there. So that means this is also, you can think that this is the energy which is responsible for keeping all the nucleons together in the nucleus. And how we get this binding energy? We have the expression for mass and energy relation as E equals to mc square. So if we want to find the expression for the binding energy, it will be mass defect multiplied by c square. So the binding energy will be equals to mass defect into c square. So this is the expression for the binding energy there. Delta M we have already calculated. We can get it from this expression, and then it is c square. So that is the expression for the binding energy. Binding energy per nucleon. This will be the binding energy divided by the mass number, so that you can get the binding energy value per nucleon. So this will be binding energy per nucleon. We have already obtained the expression for the binding energy, that was your delta M c square divided by A. Or if you write, it is your Z into MP, A minus Z into Mn minus M, this whole term multiplied by c square divided by A. So this is the expression for binding energy per nucleon there. We have the plot of binding energy per nucleon versus mass number. And if you see that particular plot, we can get many inferences and many information from that particular graph there. This is the plot of binding energy per nucleon with mass number. We have plotted it, binding energy per nucleon in mega electron volt, and here we have the mass number of the nucleons. We find the plot is like this. That means it is indicating that initially you'll find that there are certain jerk there, or for certain elements there is peak value. So it has a zigzag part there, and it is showing you peak there for certain element there, and after that it increases, it is maximum there for Fe, then it almost remains constant and falls there to uranium there. Now these peaks are indicating that these elements, they are, or these nuclei there basically are more stable than their neighboring nuclei. Like if you take these peaks are for helium, carbon and oxygen. So these nuclei are relatively more stable as compared to their neighboring nuclei there. Because their binding energy per nucleon is more, that means they have released more amount of energy there for their stability once they have formed the nucleus there. Also you can notice that initially, or for the lighter nuclei, the binding energy per nucleon value is less. For mid-range it almost remains constant there, it is high, and then it falls for heavier one. So for heavier nuclei it will fall, that means it is less. For lighter also it is less, and for mid-range it is almost constant there, and it has maximum value there for iron, that is Fe56. So here what you could see that we can easily explain the phenomena of fusion and fission from this binding energy plot. Suppose if I take the phenomena of fusion, where you have the lighter nuclei combining together to form a heavier nuclei. Now you see, lighter nuclei have the binding energy per nucleon which is less. So if they combine, in that case the mass number will increase, and as the mass number is increasing, the binding energy per nucleon will also increase. So in that case, the nuclei which they will form after getting fused, that one will have more binding energy per nucleon, that means they will be more stable. That is why lighter nuclei combine together to form heavier nuclei and give rise to the phenomena of fusion there. On the other hand, if you take the phenomena of fission, where heavier nuclei splits into lighter nuclei there or mid-range nuclei there, and there if you want to explain this one from this graph, you see the heavier nuclei have the binding energy less. So this binding energy per nucleon is less. If it splits, in that case the constituent nuclei which will be formed, they will fall in their mid-range because their mass number will get decreased. So now they will be falling in the mid-range where the binding energy per nucleon value is more than the parent nuclei. So obviously these nuclei which will be formed due to phenomena of fission will be more stable. So that is how you can explain phenomena of fusion and fission there from this binding energy plot there.